Away, Geoff.
Thank you. So, yep, my name is Geoff Perumal. Really a great honor to be here. I've been in this volume community since about 2005 when we started doing array tomography. So, seeing this group together, it's really just fantastic. Obviously, the 23 announcement of volume as one of the techniques really re-energized community. It started getting folks who weren't doing this to consider it, start to push technology forward as well. And that's really where I'm going to live these next 14 or so minutes, talking about where we're taking some of the future technologies of volume and some of the nice advancements with some currently existing tools and applying them over. So volume EM, and I probably see these movies will all play. Okay, great. There's obviously more than just the 3 techniques listed up here. We saw some great talks on micro CT, which I certainly consider a volume technique. All the TEM methodologies, traditional tomography, serial section TEM. But for all intents and purposes, when you think of volume being done on a SEM or dual beam, these are the traditional techniques: array tomography, serial block face, and focused ion beam. I've listed out some of the advantages and, air quote, disadvantages of each technique. I lived on the array tomography side, so I was a bit of a glutton for punishment, and I think we all who've done that know that story of, after hearing our samples, going through sectioning, post-staining. Great advantages, my boss was a 40-year microscopist, so the idea of ablating away materials with serial block face or fib just went against everything he was brought up doing. Archivability of AT was really important, but when you start to look into the newer technologies, the serial block face, the fib, the automation was really the big advancements of it. Serial block face was, obviously going from cured sample directly into the tool and then doing ultramicrometry approach. Then fib came along, right? And the ability to do finer Z was so valuable, but obviously that problem was the trade-off was the amount of achievable field of view, where it was more isolated towards cells instead of tissues. So that overview, which I think is probably no big surprise to anyone here, is kind of the basis for where I'd like to kind of take this forward. And it's applying a PFib into some of these workflows to create what I'd like to think of as the best of both worlds between serial block face and that of FIM. So the Helios Hydra, which is the platform for life sciences plasma fib from Thermo Fisher, offers 4 unique plasma sources, those being oxygen, xenon, argon, and nitrogen. I'll explain why I see them as more beneficial and not just cool to have 4 different species, but for volume, when you think of these 4 species, oxygen is going to be your champion. Working with plasma instead of gallium, we have a much more efficient rate of blading, which we'll discuss, and one other really nice advantage, which I'd like to keep the surprise going and for about 4 more slides on it. But as I introduce a PFib in place of a traditional gallium fib, and we just saw how valuable gallium has been in it, I think it's really nice to start off with something like this. Traditional neuro sample, prep for OTO. The size of the voxel, it's actually a little better than isotropic. It's 4 nanometers in Z, but exactly what you would expect a fib to be doing, 5 by 5 by 4. Cycle time, about a minute and a half. So I know we gear for that minute and a half. So again, it's right in the range of what we expect a fib to do. And the quality of the data, again, is right there. And I always like to start off with this because as I introduce a new approach using plasma, I'd like to start off with demonstrating how, compared to gallium, it certainly holds weight. And now we can talk about some of the nice things which plasma is able to do, which gallium cannot. And that's the higher current and as well as the way that it efficiently removes material. When you keep 2 parameters the same, in this case, we're keeping the voxel the same at about 10 nanometers, the acquisition time the same at about 12 hours. If you look at the left and the middle, what you could see is approximately a 50% increase from about 550 slices to 730, or about 30%, excuse me, of material which can be removed. So now we're talking about more efficient removal of material compared to that of gallium. But obviously, one of those downsides to some of these techniques is the slower throughput of it. So Inserting plasma, we start to see that we could do this a little bit more efficiently. Another nice thing that plasma is going to do is it's going to offer you a lot more flexibility in the sample with which you're putting into your tool. So we had a very good number of talks yesterday on sample prep, sample optimization, using that hardest resin formulation, using the OTO prep to really make sure that we're getting the most signal back to our detectors. One of the shortcomings from traditional gallium has been the actual resin which we use. Now, for most purposes, to be fair, a traditional EPON is going to be what you're using nonetheless, but there are certainly protocols where some of the acrylics would like to be applied but can't. That's because the way gallium interacts with acrylic beads. As you see here, our acrylic sample is on the left. You get that traditional curtaining effect of a gallium beam going across that of a acrylic base. By using an oxygen beam in its place, as you see here on the right, we have a much more clean surface. So that might open up to some of these workflows which allow you to do some pre-labelings, maybe imaging your thick sections of acrylic or doing post-labeling on there, transferring it in. So it's opening up to more possible workflows. Next part about it is, as I kind of alluded at the beginning, having multiple species is not just, air quotes, cool, but it's actually beneficial. Xenon is a very heavy element. It ablates materials most efficiently. And in that idea of scouting out a block face, knowing you're not quite there and needing to go deeper, as opposed to taking your sample out and going the way of ultramicrotomy, if you're relatively close, you could go the way of Xenon most efficiently, remove your material. Again, we see the effects of high current. In this case, you see a little bit of curtaining there. But switching over your species, in this case from xenon to oxygen, you have that nice smooth block face with which you would expect a fib to offer you. Now, lastly, as I alluded to, there was some magic in oxygen. So the modified preps, the putting down a platinum pad, we do all these things to help control charge, control our beam. But what we have found is by using oxygen, we're doing a great job of grounding our sample inherently without the need for a pad. So I think maybe some of you have done serial block face or fib might be used to looking at something like this initially when you look down on a block face. Block face loaded with charge. Hidden behind there is actually a retinal sample buried in resin. The reason we're not seeing it is because it's not conducting right now. And that's because we took that block, which was freshly ultramicrotomed, so we have a nice clean block face, exposing it to a beam, or E-beam that is, we're seeing a lot of charge coming back to the detector. I'm going to introduce a technique for those of you new to it known as spin mill, where we're using the oxygen beam to actually ablate away material. But the first step in that is a little bit of prep work, which basically means defining your area, aka exposing your sample to oxygen. By exposing your beam to oxygen, that sample becomes grounded. There's no platinum pad in here. You see loads of resin. But I hope what you don't see is charge. This is going to allow us to work at the most optimal acquisition parameters. Again, no platinum pad on here. We're not going the way of low vacuum, so we're keeping our acquisition speeds the best. We're keeping our minimal dwell time the best. And all the while, we're doing this with a serial block face field of view. So traditional fib, I don't know what your all thoughts were when you first got exposed to how a fib's geometry is, and now Chris kind of pointed out a different geometry with that L-shaped formation, but the idea of creating a trench, putting your platinum pad down, just went against everything which I knew or expected a fib to be when I first discovered the idea of fib technology. I figured your focused ion beam was going tangentially across your block face, removing material, exposing it, similar to that of serial block face. But then what you find out is the brilliant and crazy geometry that goes into a traditional fib, tilting your sample, creating a trench, imaging off axis. Well, what spin mill is, and I'm going to try to play this movie, that's quite all right, is just that. We are taking our block, which we see here, and imaging it, or ablating away essentially tangential to that block face at a slight offset of about 4 degrees, exposing a field of view comparable to that of a serial block face tool, up to about 1 millimeters field of view, all the while maintaining the benefits of fib resolution and Z, down to practically 10 nanometers. If your sample is really nice, probably 5 nanometers can be squeezed out of it. So the name spin mill is a bit of a misnomer. The sample does not continuously spin around your plasma beam, but rather there are 5 72-degree rotations denoted by each of these arrows. With each rotation, we do a rastering with the plasma beam, opening up a block face. 5 times 72 will give us that 360 degrees for full rotation. And now what it's going to expose us to is this large field of view, again, thanks to the efficient way that plasma ablates away material. So now we're talking, in this case, in this example here, we're looking at about 650 micron cross section. So again, vEM tends to be in the tens of microns field of view, maybe up to 100 if you're a really skilled operator. So now we're operating in that domain of a serial block face. This is one of those typical approaches which you could do for a single ROI serial block face. The spin, by the way, I should take a step back and point out, is basically the idea of pointing your block face directly at the fib beam, creating a circle, which is basically your spin zone where you're going to do your acquisitions. And you can kind of see the outline of it in that first image in the top center. Then that typical process which you would use in serial block face comes true. Clean up an area, identify, and then do your highest acquisition or highest resolution acquisition, as we see here in the middle left or middle bottom. Now, the other thing which I'll point out very quickly is it's also like serial block face in the sense that we can do multi-ROI. Again, with a fibs resolution. So when we open up an area here, I want to quickly point out to you here is this overview, and here is the spin zone here. You could see, for demonstration purpose, there are actually 2 trenches which were milled, turning your block to cross-sectional fib. All of that is time on the tool. So it's cleanup work, it's cleaning your face, it's putting down a platinum deposition pad. So a reason I point that out is there's a lot of time saved when you don't have to do that intermediate but necessary work in traditional cross-section. And you could rather just clean up and go right towards your acquisition points of view. So as I pointed out a few times now, multi-ROI, similar to that serial block face, is completely an option on this table because we have such a large field of view, meaning each ROI can have a consequential X and Y field of view, meaning that we're pulling lots of data from an individual ROI without having to cut lots and lots of trenches. That's kind of nicely noted here. We could see in the upper left a large field of view exposed. In this case, there were 3 different ROIs. It's as flexible as needed. You can do large fields of view, high pixel density. You could do the reverse, a small field of view, low pixel density, although I guess in fairness, it'd probably be the opposite way. But the 2 can be combined as well. And now here's a little bit of fun data which we've acquired. I apologize in a few seconds, it's going to pixelate, but what we're looking at here is 25 by 25 by 15. So decent resolution across a field of view of about 250 microns. Lots of open resin in here. What we're not seeing is any charge. And again, that has to do with the fact that this has been exposed to oxygen. So excuse that pixelation there. But whether it's the completely open resin or the granules, we're visualizing it without any gases or any mitigation. So we're really seeing that truest data from the sample. Last little bits here. Obviously, as I'm sure you can imagine, we have the ability to turn this down the pipeline towards the data part of it. So we're looking at some muscle here. We all know from cross-sectional imaging, obviously, there's a lot of mitochondria involved in muscle. When you're able to image at large fields of view at high resolution, we can really start to understand just how intricate the mitochondria, which is exactly what was segmented out here, is in a muscle sample. That can be funneled down into a analysis part of it. So it's not just a pretty picture machine, it's actually offering meaningful data. Difficult resins, as I alluded to, this does have the ability to handle as well. This is, to me, what's really impressive about this is twofold. One, this is another acrylic example. My movie on this was really failing this morning, so I have some stills, but I'm going to present later this afternoon and have the luxury of switching over to VLC player to show you the movies on this. But this is high pressure frozen, freeze substituted in the absence of osmium. Yeah, we're getting what I would call pretty strong contrast, quite dilute osmium in here as well. Last little bits, putting some of this together. We're talking about a fib and a serial block-based like approach. What you do have the ability is to switch over. If you did need that smallest voxel, you could scout out, as you see in the upper left, an area, define it in this big green box. If you needed more than a traditional 10 by 10 by 10, if you needed that 5 nanometer voxel, you have the ability to rotate your sample 90 degrees, put down that platinum pad if you like, an image down at about 5 nanometer voxel. So I like to think of this tool as that complete offering for volume in SEM, whether it's AT, traditional fib, or even the serial block-based like approach. And I will wrap up with a bad pun. Probably this will resonate with a lot of you. I'm guessing you've all spent a lot of time in front of microtomes looking at muscle. And I'm sure you've seen this when you've done your tableau sections, which is muscle-oriented 90 degrees wrong. And now here's some of the nice things about imaging isotropic voxels is as we pan out and forgive the 540 degrees of rotation that you're going to see here, is acquiring at an off angle should be less of a problem when you're doing it isotropically. That's because as we go through what will become XZ in about 180 degrees, we're going to see the perfect banding of the muscle fibers exactly as you would expect it, without the need to take your sample, reorient it 90. So I will let that play, and let's look down that nicely. And in the interest of time, I'm going to just speed this up here and just give you a little food for thought, which is as we think about these techniques for volume EM and in SEM, I think we should certainly start to consider spin mill in that option as well. So with that, thank you all for your time, and glad to answer any questions if there are any.
Thanks, Geoff. Very interesting. Do we have any questions for Geoff?
Interesting talk. I was wondering about the effects of the oxygen plasma on preventing charging. Isn't that just because you actually oxidize the entire sample and that it then becomes conductive?
Yeah, there's certainly some embedding of the oxygen into it, absolutely.
That would also mean you mentioned, I think halfway down, that would be potentially possible to, for instance, do some labeling on the milled surface. But if you oxidize the surface, then that's no longer possible because you're killing any antigens that would probably be there.
Sure, sure. And I guess if I should take a step back and say it would be in a stepwise approach in that workflow, which would be prior to SEM imaging.
So, any more questions?
Yeah, thank you. I'd like to also return back to the charging and my previous question to Chris. So you talked about oxygen, that it, reduce charging. So what are the ions? So they do the same way, and then is it the same effect that we see on the gallium ions that they also somehow, gets accumulated on the surface during milling and then just reduce the charging?
So the other ions, there is a similar effect. I think there's a cost benefit of using the oxygen in terms of ablation rates, charge, a little bit of etching in there as well to kind of minimize the topography of the image. As to it versus gallium, it's tough to say. I've never seen a very big cross-section manuscript of it. So it's certainly probably there is some grounding on there as well, but pretty proud of this one.
Okay, well, I think if there are no more questions, let's thank Geoff again and let's move on.